Okay, I guess we can start slowly. Again, our goal is sort of, to go deeper and study further properties of the Lagrange transform. And, at the end of the day, there are going to be certain properties that we can, you know, like we can just enjoy and remember because certain properties are really beautiful. um Whenever you need proof, you can just come back, and check out the notes and stuff like that. uh because I do the same thing because typically I wouldn't be able to memorize everything in my mind. So I recall here the Lagrange transform we recorded already last time. And maybe, this was a summary of what we did, but maybe I would just say that if H is convex, I'm just writing down what we have, then we would have that L equals to H star, and L star, which is H double star, is gonna be goes back to H itself. um, Again, if you check back the proof, we didn't need to use the superlinearity of the Hamiltonian there. You know, this one works for any kind of duality. And then if you have in additional that H is superlinear, then you would also have that L, which is H star, is also superlinear. Finite property is hidden here. When I write superlinear, then I just mean that it's finite already here. Um, and that's pretty much it what we proved, for the standard step. And this is sort of like, as you have, if you have learned PD1, this is sort of basically in chapter 3 of Evans. And then as I said, we plan to go further. The second thing that we proved last time is that if H is convex and H is only differentiable, then automatically you have H is C1. That's pretty beautiful. um, Okay, I have a question for you guys. This is not related to anything, but whenever we are curious, if you feel bored, you can enjoy. Um, you know, this one is telling us that if you have a convex Hamiltonian, then you can recover it by doing Lagrange transform twice, right? So a natural question would be, so if H is not convex, you know, enjoy it, then what is H double star? Okay, it's a natural but beautiful questions, and sometimes research in PD in analysis are driven by research directions are driven by those very natural and simple questions. In other words, when can we recover? You can think of it as an inverse problem, right? You can do observations and taking the supremum, stuff like that. You cannot observe the function itself, then can you recover your function? That's sort of a natural question to ask. Okay, so this is just for fun. If you're curious, like why would we need convexity here, right? Okay, so that was just the recap of the previous lecture. We're gonna do more today, as I promised. Um, and for today, we're gonna prove this surprising property. Um, Again, it's just rather surprising to me as well. Again, when I first saw it, but of course, when you get used to it, then it's just natural. Um, so what it says is that, there was a second line in the middle here, but what it says is that if H is strictly convex, I'll explain to you why. I wrote down the definition here. I'll explain to you why in the sort of like cartoon of what I'm drawing. Sure. Um, then it is equivalent to saying that the subgradient sets a disjoint for different values of P. Okay. And what is really surprising is that it tells us that this is equivalent to the fact that the Lagrangian is C1. So, like strict convexity of the functions implies the Legendre transform is C1. So this is quite surprising, right? Um, at least, I mean, it's not clear if we just look at the definition. Okay. So, so strict convexity here, when you in the pictures, that means that if you take the two values of any point p1 p2, and maybe this would be h of p1, h of p2, for any 2 point p1 and p2 here, then you draw a line segment. If you draw a line segment from h of p1 or p1 h of p1 to p2 h of p2, if you draw this line segment, then the graph of the line segment in the between is strictly below it. Okay, so if you take any point here, any point ps, which is the convex combinations of that, so sp1 plus 1 minus sp2 for 0 less than s less than 1, then you would have strictly that h of ps is strictly less than s times h of p1 plus 1 minus s times h of p2. Okay, so that's sort of the meaning of strict convexity. um, okay, just the picture, there's nothing more than that. Okay, so let's do the proof, and then I'll explain to you a bit of the geometric meaning, at least in 1D. You're gonna see. And and again, what is really striking here is that strict convexity, meaning that okay. So let's see. Okay, maybe even when you look at the, so in the 1D case, look at the above graph. Let's try to imagine what strict convexity means, okay, before we do the proof, because I wouldn't want you to get lost. So basically, strict convexity meaning that if you take any points and you take the sort of tangent vector, assuming that everything is nice. I don't assume the Hamiltonian here is C1, but let's assume that everything is nice. So if you touch the graph by supporting hyperplanes, right, supporting tangent plane in this case, strict convexity means that for P1 less than P2, I should have that H prime of P1 is less than H prime of P2, right? In this graph, right? Because otherwise, if they are the same, then you would have a line segment there. So basically, H prime is sort of increasing, strictly increasing. And that tells you that the second claim holds true, right? The subgradient sets are disjoint for different values of P. And from that, we can imply that L is in C1 very naturally. So that's, the first sort of like first touch of geometric interpretation. We will come back for that a little bit later. Okay. Um, so now let's do a proof of the result. Um, so as always, when we prove equivalent claims, then we try to find ways to prove this one imply the other, and so on and so forth, in a circular way that everything is equivalent. The first thing we prove is that one implies two. So one is the fact that the Hamiltonian is strictly convex, and we need to show two holes. That means that if I take P1 different from P2, then the subgradient sets have to be disjoint. So we prove by contradictions by assuming vice versa, saying that there are two different values of P, so that the subgradient sets intersect at least one point V, right? And again, basically the picture tells me, at this point P1, I have a supporting hyperplanes of something like V, right? And in 1D of slope V. And then at the other point P2, I also have a supporting hyperplanes of slope v as well. So seemingly, for the graph to be convex, then seemingly it has to have a line segment there, right? And that's the contradiction to the fact that the Hamiltonian is strictly convex. Okay. So now we have to write this one down, but that's sort of clear, right? Because the key point was that we take 2 points, P1 and P2, and we are taking points in the between, in the middle, and we show that it has to be essentially a line segment in terms of the graph of H, okay? So that's exactly, I wrote down again the definitions here. For any point P, by convexity, I have this holds at P1, because V is in the supporting hyperplane, and then, or I mean, this is the right-hand side and affine function is a supporting hyperplane. And in particular, for these relations, you just choose P. You choose P as the test point to be exactly the point in the middle here, right? Exactly the point in the middle. And you plug in the relations. So on one hand, you have H of PS is greater than the right hand side. When I do subtractions, P minus P1 is just gonna be coming this one. You can just do algebraic calculation here. It's clear, right? And then similarly, you have H of P is also greater equals than H of P2 plus S times V times P1 minus P2. So you see that there's a relation here between, there's a relations in the two terms here. I have, 1 minus S times V dot with P2 minus 1 and S times V dot with P1 minus P2. So if I do a correct way of convex combinations, those things can cancel out, right? Right? And the correct convex combination is to multiply this one with S and multiply this one with 1 minus S and sum them up, right? And then when you sum them up, then you ended up with exactly that, exactly that H of PS is greater than equals to S times H of P1 plus 1 minus S times H of P2. And clearly, by convexity, you have the other direction, right? So when you combine them together, you need to have equality, which is exactly this picture here, right? Exactly this picture here. So hence your graph is a line segment there. It wouldn't be strictly convex. So strictly convex just telling us that 2 points wouldn't have the same supporting hyperplane, right? Essentially, that's sort of a way to think about that. So we have one implies two. Okay. All right. Again, tell me if you have questions or concern. All right. Now let's prove the other direction. So that's that. Now we need to prove 2 implies 1. Okay. Again, this might not be the smartest way, but it's a uh, clear way. So I when I write down the lectures, I chose, according to me, the most intuitive way to explain things. They might be a little bit longer than the most economical way, but they're useful. All right. um so to go vice versa, we assume that H is not strictly convex. That means that we can find a line segment so that the values of H is also a line segment, right? So what we are saying here is that if you connect the 2 points on the graph, this is P1 H of P1. If you connect it with P2 H of P2, then everything in the between here is exactly PS H of PS. So forms exactly a line segment, right? In terms of the graphs of H. Okay. Um, because we assume that it's not strictly convex and we want to come up with a contradiction. All right. So what do we do here? Okay. All right. I mean, you can say that this is not natural, but you can guess. You just guess things. What we do here is that you choose any point in between. I mean, it needs not to be just h of p1/2. You just choose any point in between. Why is it good to choose a point in the between? Because if you choose a point in the betweens, you have two reference points to compare with. Um, so again, just for easy algebraic manipulation, I chose a p1/2. So pick a v in the subdifferential of h of p1/2. Then you write out the definitions, right? This is just the normal definitions that, because h of p is always greater than equals to the right hand side. uh, Not a big deal here. Everything is normal. Okay. um, and then in particular you picked you pick p equals to p1 in the above relations. You plug it down, I mean, not plug it down, you just replace p to be p1 here. Okay. So if you take p to be p1, clearly you have this is just h of p1, nothing. H of p1/2, as we said, is 1/2 of h of p1 plus h of p2. V dot with p minus p1/2, and when we chose p to be p1, then we would have nothing but v dot with p1 minus p2 over 2. Okay. Uh, So, after cancellations, cancel things out and multiply things with 2 or something. Then you have h of p1 is greater than equals to h of p2 plus v dot with p1 minus p2. And this is already a good signal, right? Why is it a good signal? This suggests us that, okay, this is a good signal that suggests us that v is in a subdifferential of h of p2, right? um, that's a very good signal already suggesting us that. And it's also clear from the picture, you know so let's say from the picture I drew here, let's say that, okay, maybe let me change this one to p1/2. So in the picture I have, this is p1/2 and h of p1/2. In this picture, how do I choose a supporting hyperplane? It has to be below all those points on the line, right? So in 1D, okay, in multi-D it can be different, but in 1D, if you do that, then your supporting hyperplane must be just this one, which has slope V, right? Exactly that line. So it suggests that V is also in the subdifferential of P2. And indeed, you just check it out. I mean, you just combine these relations. So what do you do here? Um, you just take this one, you combine with this one, the two relations you combine to get down. You just replace h of p1, in the thing up here by these relations, right? I have h of p1 here. I change it by something less than that, so everything is fine. So if I do it like that, then 1/2 of h of p1 plus h of p2 just becomes h of p2, right? So I have h of p is greater than equals to h of p2. And then I have v dots with something. And you can see that I have v dots with this one, which is natural. It just comes uh, from just p minus p1/2, right? And then v dot with p1 minus p2 over 2, which is exactly that, because I have 1/2 up here. So I needed to have 1/2 down here. Okay. So after rearranging things, I would have h of p is greater than equals to h of p2 plus v dot with p minus p2 for all p. Okay. So that implies that, as we said, so we would have that v is in the subgradient of h of p2 and v is also in the subgradient of h of p1/2. And this is a contradiction, right? Because our assumption on part 2 was that the subgradient sets are disjoint for different values of P. So it's beautiful, like uh, going from one to the other. So to sum up, in terms of geometrical meaning, strict convexity telling us that the supporting hyperplanes have to change the slopes for different values. In order for the functions to bend up, then your supporting hyperplane have to change the slopes. And this is actually related to curvature, right? I mean, if you think about curvature this way, it's the same, right? Okay. So in a way, what we are doing for subgradients and subdifferential sets and stuff like that here is also useful in certain geometrical aspect of Monge-Ampere equations. So the preparation here is also useful for other other research direction. Okay. So now eventually we already let's say that we already proved that 1 is equivalent to 2. As you said, I said that this is not the most economical way, right? We have to prove more directions than we would normally do, but that's fine. So to prove the theorem, then we need to prove the 2 is equivalent to 3. And as I said, this is our favorite inequality. We're gonna use it pretty much quite sometimes, maybe every lecture. Maybe I'm wrong, maybe in lecture 22, then I'll pull it out, not in our lecture anymore, but whatever. Okay, so this is our favorite inequality, and then equality is also of our favorite. It happens if P is in the subgradient of L, and V, or equivalently, V is in the subgradient of H as P. Okay, so that's natural, and the other thing I need to say is that 3 is exactly saying that L is in C1, but as L is convex, this is equivalent to just showing that L is differentiable, right? Exactly the preparation step that we did earlier. We just need to prove that L is differentiable. So if L is not differentiable at a point, then that means that I can find 2 different values in the subgradient sets of L, right? So if I were to draw a picture, then maybe it would be like that. So if this were V, I would be able to find 2 different points, 2 different values in a subgradient set. I mean, here I drew they represent for the slopes. Okay, then you would be able to find 2 different slopes here. And if P1 and P2 are in the subgradient sets of L, then remember the duality, the equality is amazing here, is that this is equivalent to the fact that we would have that V is in the subgradient sets of both H is P1 and H is P2. Okay. And this is equivalent to the fact that, the subgradient sets of H are not disjoint at different values of P. So we are done. It's amazing. Again, I mean, again, of course, we are sort of like putting lots of time here for various sort of preparation steps. And as I promised, in our class, I'm going to go very slowly, not very, we are not wasting our time, but slowly enough for us to enjoy and also to see the key points. At the end of the day, there can be certain technicalities that you are not used to. Sometimes we might just have to take something for granted, that's fine. Research is vast, but many of the times, we can see that. So I mean, to sum it up, how should I phrase two is equivalent to three? So to put it this way, if L is not differentiable, then it is equivalent to the fact that there are two different values, P1 and P2, that are in the subgradient sets of V. And still from this picture, this is equivalent to the fact that del H of P1 intersect with del H of P2 contains at least V, because that's a duality. The dual relation is that P is in the subgradient of L at V is equivalent to the fact that V is in the subgradient of H as P. Um, and that's it. That's the proof. Okay. Um, yeah, maybe this one I already said it out loud, but in one day, the other way to think about a picture proof is that this is a general picture where you can have line segments, but the key observation was that if P1 is less than P2, and if you take 2 points V1 and V2 in the subgradient, then V1 should be less than or equals to V2 in one day, right? Because it's changing like that. Uh, Surely you can have equality, but equality happens, and I would say, and V1 equals to V2 if and only if H is not strictly convex. So that's it. Yeah. Um, yeah. So that's good enough for the first result. And again, I would say that it's rather surprising, right? Because strict convexity of a function implies that its transform is C1, in a way. They don't seem really related, um, right? In a way, if we seek very deeply about the duality, then they're related, but not immediately. Any concerns or questions here, or are we good? If we are good, then I'll go on. Or if you have discussions or something that's not clear or anything of concern. No, we are good. Okay, cool. You know, again, for this class, I really enjoyed it. At least I feel really at ease, and then again, we can really learn new things. I'm surely under pressures of doing good lectures and useful things for us, but I'm not under the pressures of having to make sure that everyone is on the same page like undergraduate classes. I'm teaching also 619 after this, and then all the students turn off their webcams, and sometimes I was like, are you with me or not? I was like, but anyway, all right. Um, and then there's the definitions of something stronger. So stronger here, meaning that, so I would say, okay, let me put it this way. So we have a chain of relations. So convexity is weaker than, okay, I'm writing this in a literal way. This is not true, right? It's not less than equals to, but this is, uh, you know, uh, so convexity is convex H is not as strong as strictly convex H, and strictly convex H is also, less than uniform or locally uniformly convex H, and also this one is less than equals to uniformly convex H. So this is a chain of relations of convexity we are considering, because you see that strict convexity, we already require something stronger, right? And locally uniformly convex is even a bit more than that. Um, so the definition is here. So locally uniformly convex. I'll explain to you what do I mean by locally. I mean, I'm trying to be careful. Um, so what it means is that if you take the Hessian, then it's gonna be it's if it's C2, and if you take the Hessian, it's always positive definite. Okay. And for those of you who are not used to what I'm writing, then I can write out more analytical definitions here. What I mean is that that is for any vector C in Rn, I would have that H of Pi, Pj, and P multiplied with Ci multiplied with Cj is always greater than 0. Um, so here C is C1 up to Cn. Okay. So basically, this is just a quadratic form, right? The Hessian is an n by n matrix, and this tells us that C2 is symmetric, and positive definites means that all um, all eigenvalues are positive. Okay. So locally uniformly convex is stronger than strictly convex. So, okay, why I'm careful here? Why do I only put locally uniformly convex? Because it's greater than 0, but when P goes to infinity, for example, it might get very close to 0. Okay. Um, so example for, locally uniformly convex H. If I'm not mistaken, you can check me. You take H of P is 1 plus P square to the power 1/2. Okay. Sometimes, people would say that this is a Japanese bracket, but I mean, it's just this formula. This one, I believe that is locally uniformly convex. It's a cone, but at the origin is smooth, right? It's not like motor P. It's smooth. And when you let P goes to infinity, the second fundamental form, or I mean, or the Hessian is getting less and less positive. Okay. And then the second one is that we say that H is uniformly convex, and this turns out to be mostly used later on. Very strong assumption, but it's good for us. So H is uniformly convex if H is in situ, and we can find a number theta greater than 0. Don't worry, I'll remind you whenever there's a need, so that the Hessian of HP is greater than equal to theta times In for OP. What I mean here is that um, the n by n matrix here, the Hessian is positive definite, and all eigenvalues greater equals to theta. Okay, and or you can also write it in a more analytic or analysis way, H of P I P J P. I'm sorry, I'm using the Einstein summation conventions here. So repeated indices like I and J, meaning that I'm summing over I and J. Okay. So H of Pi, H of Pj, Ci, Cj is greater than equal to theta times the length of C square. Okay. Yep. Okay, good. Okay, so let's see. Yeah, I think we have exactly enough time to prove this result, and then maybe at some time to discuss. And it's good we are done with the first work smoothly. No glitches in terms of technicality. So the last theorem, I mean, this is very easy to memorize. I mean, and I barely proved this. I mean, this is one of my first time proving this. I mean, I have proved this before for others, but I barely prove it. I'm just taking it for granted. Okay, and you can also take it for granted is that all the preparations we did earlier was for this result, that if h is in ck, so smooth enough with k greater than equal to 2, h satisfy h, meaning that this one is this one just means that it's convex superlinear, and h is locally uniformly convex, meaning that is um, this one means that surely we have that d squared h as p is positive definite. Okay, then we have exactly the properties for h is preserved. That's beautiful. I mean, you're gonna see why it's beautiful. Then L is also in ck. Okay, and the derivative of h, so the gradient of h is a ck diffeomorphism from Rn to Rn. Okay, so it's really a diffeomorphism from Rn to Rn. And then you have a bunch of properties listed here. The gradient of L is the inverse of the gradient of H. The Hessian of L is the inverse of the Hessian of H, computed at the correct value. And the third one is this one is not too much. The third one is just coming from the so this one is just from the Legendre dual inequality. That's not much. Okay, and exactly you can see the proof is here. So so you can see the proof is here. So first of all, what do we have? Okay, maybe so let me outline it and let me tell you what do we have. So what do I mean here? So by the previous theorem, right? I mean, we have d squared of h as p is positive. Then okay, I'm gonna ask you to do this one just for fun. A question here is that from here, show that if d squared of h at p is positive, I'm gonna post this question for you to discuss. Okay, then show that h is strictly convex. I mean, this is rather clear, right? But we need to write down this. So if it's locally uniformly convex, then H is strictly convex, and then H is strictly convex, and by the previous theorem, L is in C1. Okay, why do I need to L is in C1 here? Well, because I want to use this dual inequality here, right? And then I want to see when do I have equality happens. And when H and L are C1, then I can talk about gradients instead of subgradients, right? So that's easier for us. So equality happens here. Then instead of talking about subgradient, then I can talk about actual gradient. So P equals the gradient of L at V, and equivalently V equals to the gradient of H as P. Okay. And clearly from here you can see the reverse thing, right? Because you have P equals to dL of V, which is from this, and from the other one, because V equals to dH of P, then you can see that P is dH inverse of V. Okay, and that's give us the first relation. So dL is the inverse of dH. And then because H is locally uniformly convex, d squared of H is greater than 0. Then you see that by the inverse function theorem, right here, right? If you take the determinant of this one, clearly, I mean, to use the inverse function theorem, you don't need the second the Hessian to be positive. You just need the determinant to be not zero, right? to have the inverse function theorem. So by the inverse function theorem, you have that dh is a ck minus 1 diffeomorphisms from Rn to Rn. Okay. So if you have that, okay, so then you have also the dl from Rn to Rn is also a ck minus 1 diffeomorphism, right? And that implies that you have L is in ck. So it's beautiful, right? You know, you infer from the fact that dh is the inverse of dl, and if dh is ck minus 1 and dl is ck minus 1, and that implies that, you know, L is ck. It's beautiful. And to prove the fact about the Hessian, then you just need to take the fact that dh composed with dl is the identity map, and if the identity map, then you just use the chain rule, right? You differentiate once more. You have the Hessian of L is inverse the Hessian of H. Okay. And finally, we are done here, right? Because you have equality happens when P equals to dl of V. So you replace in the above inequality, you replace P by dl of V, right? To have equality, then you have H of dl of V plus LV equals to dl of V dot with V. And then you imply that L of V is this one. LV is V dot with dl of V minus H of dl of V. Okay, then we are done. All right. So I have just a tiny remark here. Tiny remark is that if we use this formula, we're gonna use this formula a lot. LV equals to V dot with dLV minus H of dLV. Then it's not very clear that L is CK. Then it's not so clear. Right? Why I'm saying so? You know, you have H is in CK, but DL you only have that is in CK minus 1, right? So you have DL is in CK minus 1, DL CK minus 1, H is in CK, right? So you combine a bunch of CK and CK minus 1 functions, and magically you have L is still in CK. So there's certain cancellations happening here, right? The cancellations is beautiful in a way that it preserves the fact that you lose nothing about the differentiability under the Lagrange transform. Okay, you need to start with k greater or equals to 2 here, but it's totally preserved. Okay. Yeah, I think that's pretty much it for today's lecture. I'm gonna post just a question here for you to discuss for fun. You know, the other question we already discussed it, but I'm gonna just post them and take a picture anyway. So just this question that you know, for us to understand a bit more. And eventually, when we have enough of questions, and I'm just combine them to give you a problem set, and you work on that and turn it. You know, that's all. I'm not thinking of this class as something like you have to spend a lot of time to prepare and do the homework. This is rather ideas and thing to do research, you know. Any concerns, any discussions, or anything you want to add?
So I just had a question. So are there like any stronger results when you have like the stronger condition, the uniformly convex? Like,
oh, okay. That's a good question. Here, because you see that the convexity and the transform we are using here, the diffeomorphism and stuff like that here, um, you can think about it in terms of local results. So that's why locally uniformly convex is enough. Um, Later on, I mentioned that we're gonna do more for the uniformly convex case. The reason is that if somehow you can have certain a priori estimates that it doesn't matter that you have to worry about OP, but you only have to worry about like P in a bulb center 0 radius 1000, for example. Then in that ball, the Hessian is positive definite, is continuous, and it has to be uniformly convex in just that ball, right? And that's
See.
enough. Yeah. So later on, you're gonna see that if we have certain a priori estimates, then locally uniform convexity is same like uniform convexity. Um, um, so uh, so I would say that this theorem is pretty much what we need. For Hamiltonian and Lagrangian dynamics. This is something that we can use to transfer going between the two. Um, and you really don't need to memorize the proof or anything, Uh, you know, I forgot whatever the results or the proofs I wrote down very quickly. Just the mechanisms and the ideas, and we can always reformulate what we have in our minds. Yeah, but yeah, that's very important actually. But for us, many times that we have a priori estimate that helps us to go from locally uniformly convex to uniformly convex cases. So that's fine.
I see. Thank you.
Okay. Any other concerns or anything uh, of particular? Um,
Um,
yes.
for the question that you asked about locally convex implies locally uniformly convex implies it is strictly convex.
Mm-hmm.
Is that equivalent in if we make an additional assumption that it is C2?
That's a good point. Why don't you try to answer that?
Okay.
Right? Again, as I said, it's pretty much everything is driven out. Mathematics for us is pretty much driven out of our curiosity, and yeah, that's a good question. Why don't you think about it? Yes, but it's clear that you're right from the beginning, that strict convexity, then we don't need to assume anything about differentiability of the function, right? Uh, so your question is very valid. That I'm gonna add it here. I mean, again, as I said, I didn't. So if you assume that H is in C2 and strictly convex, then can you imply that H is locally uniformly convex? Right.
Yes.
Yeah. So that's very good. And why don't you think about it? And then I'm gonna post this question on Canvas, and then you guys can have fun discussions. Again, I don't want you to feel that this is a burden, that you have so many things to do, and especially for all of you here, I think that you have some research problems in your mind. But I want to use this one as a booster, like just certain aspect, maybe having fun, when you feel bored, you can just enjoy it.
Thank you.
Yeah. Okay. If there's nothing else, then have a good weekend, and stay safe and healthy, and still getting out a little bit and enjoy the snow. More is coming. Thank you. See you.
Thank you.